Any unauthorized reproduction, use, transmission, or delivery of the materials contained herein, in whole or in part, without the express written permission of Educational Activities Video Incorporated, is forbidden by law and subject to penalty.
Soaring mountains, dense forests,
oceans stretching to the horizon, cities reaching toward the sky.
All around us are countless stunning scenes, the result of billions of different materials, made from just a few chemicals that make up our world.
Chemistry is the study of these chemicals and how they make up our planet.
The basics of chemistry. Every day, you come in contact with hundreds, even thousands of things. They may come in different shapes and sizes and look and feel differently. But all these things are essentially alike because they are comprised of basic chemicals that scientists refer to as matter. Matter, as defined by scientists, is anything that occupies space and has weight.
These objects, for instance, are examples of matter because they obviously have weight or mass and clearly occupy space or have volume. Light and electricity, however, are not matter. Why? Because they do not have any mass that you can detect, nor do they occupy space.
In this program, we'll start by discussing what scientists call the states or phases of matter.
Next, we'll consider some unique structures of matter, that is, elements, compounds, and mixtures.
And then conclude with a look at some of the properties of matter, including density and weight, along with other physical and chemical properties.
To start, let's take a look at the different states or phases of matter. In our daily lives, we see, touch, and feel many different things that are all forms of matter, and that can be classified according to certain physical characteristics that set them apart. Let's think for a moment. What are some of the physical properties that you recognize in these examples of matter? Apples, a vase, a deodorant spray, or a bowl of soup. Now, to take another look, physical properties you can easily identify with a red apple are color and taste. With a green vase, the characteristics include its color. And the appearance of the vase, of course, is that of a solid object like the apple. And for the bowl of soup, physical properties you might cite are taste and odor. The soup is neither a gas nor a solid, but a liquid containing some solids. For the deodorant spray, the physical properties include odor. Here, we have a spray which is not a solid, like the vase or apple, but is instead a liquid propelled by a gas.
In our world, the appearance of matter is constantly changing, as you can see with this icicle. What is happening to the ice here? The ice is melting and dripping. As you can see, the ice, which is a solid object, is becoming water, a liquid. What will shortly happen to this water? In a short while, the water melted from the ice will probably be heated by the sun and evaporate as a gas. The ice, the dripping water, and finally the water vapor are all made of the same substance, but they are in different physical states or phases.
The appearance of matter, then, is constantly changing. Consider these fireworks, for example. What changes in physical states does one of these firework devices go through? First, the fireworks device is a solid object. Then, when ignited, a portion of it becomes a blazing, colorful gas.
For scientists, learning how to predict when and how matter will change is very important, because understanding how matter changes has helped scientists develop many new products, such as plastics, nylon, and life-saving medicines. Indeed, the different states or phases of matter provide a framework for scientists that enables them to classify the different kinds of matter in the world. According to this classification, matter can exist in 4 physical states: solid, liquid, gas, and plasma.
Look at these things: a rock, a baseball, a crystal. All of them, of course, samples of matter. But what do they have in common? They are all objects and serve as several examples of a solid form of matter. How do you think scientists define a solid?
Scientists define a solid as anything that has a definite shape and a definite volume. Unlike liquids and gases, solids can often be carried from place to place without a container.
Now, look at these containers of all different shapes and sizes, filled with another kind of matter, liquid, in this case, water. As we see here, liquid takes up space. It has volume, but it has no definite shape. In fact, liquids take the shape of any container into which they're poured. Here, we see a beaker and a graduate cylinder, each with the same volume of liquid. But the shape of the liquid is related to the container. So scientists define this next form of matter, liquid, as having a definite volume but no definite shape.
Sometimes we may have a party balloon filled with helium. If we untie the balloon, it deflates. What is the substance that we let out of the balloon? Is it a solid? Is it a liquid? Obviously, it is not a solid or a liquid. The substance coming from the balloon is a gas, another form of matter. Using the terms volume and shape, how would scientists define a gas? Scientists define a gas as having no definite volume or shape. As the gas leaves the balloon, we feel a rush of air, but it eventually spreads throughout the room. But can gas have volume and weight? Let's find out with this balloon, which we first see deflated on a scale, with very little weight registered. But when we inflate the balloon with gas, what do you observe? Filled with gas, the balloon now registers a greater weight on the scale. So, as we've seen, a gas can occupy space and definitely have weight.
Here, we've got a typical school lunch. Take a moment and see how you would classify the different items here, as solid, liquid, or gas. From the lunch, The items you could classify as solids are the chicken, the broccoli, the fruit, and the meat in the soup. The liquids include the soup, milk, and tea. And the examples of gas include the vapor from the soup and tea.
The fourth state of matter is what scientists call plasma, and is more difficult to visualize than the other phases of matter. Plasma, like gas, has no shape or size, and is rarely found on Earth. But matter in the plasma phase exists throughout the universe. According to scientists, plasma is associated with unique particles that produce large amounts of energy. For example, most of the material that makes up the sun and other stars is matter in the plasma phase.
Having discussed the different states of matter, let's now consider the structure of matter. People often organize or classify material for easier reference. Thus, you might sort items into a file cabinet, a collection, or even a library. In a similar manner, scientists divide the material in our world into states of matter, that is, solids, liquids, gas, and plasma. But as we've discussed, these states or phases of matter are not enough, because one kind of substance, such as water, can be found in more than one phase.
So, to be more specific and avoid confusion, scientists classify matter by its purity, as well as its physical state. Scientists who work in chemistry, known as chemists, examine the minute particles that make up substances. When the particles are all the same, scientists call the material an element, as with this piece of copper wire. A pure substance like copper contains only one element. This element is composed of countless identical particles called molecules, which in turn are each composed of still smaller but identical particles called atoms. This piece of copper, for instance, is a pure substance with only one kind of atom, the atom of the element copper.
Running, walking, resting, the air you breathe contains oxygen that makes your life possible. Oxygen is also an element, composed of identical atoms. Here, we see what's known as the periodic table, listing the chemical symbols of all the elements discovered by scientists. Listed in the table are more than 100 elements, with 92 of them found in nature and the rest man-made.
Thus far in the program, we've looked at the states or phases of matter and discussed elements as an essential part of the structure of matter. Now, for a review question, go to activity sheet number 1. The window glass we see here looks like a solid. But in very old buildings, the bottom of the glass panes appears thicker than at the top. How can you explain this observation? Turn off the player to answer the question. Then turn it back on when you're finished.
Here's the correct answer for the exercise you've just completed. Interestingly enough, glass is not a traditional solid. Instead, according to chemists, glass is a very thick liquid that over time will flow downward. Silver is another example of an element. But like other elements, such as iron, lead, gold, and copper, silver is relatively difficult to find in nature. The reason for this is that many of these elements react with each other to form more complicated chemicals called compounds.
A compound is two or more elements chemically combined to form a new substance. For example, the table salt we often use with food is a compound. Compounds have both chemical and physical features which are different from the elements in their makeup. Table salt, for instance, is composed of solid sodium and chlorine gas, both of which are dangerous and unstable elements. To demonstrate how unstable and dangerous sodium is, notice what happens when a small piece of sodium is placed in water. The sodium begins to burn rapidly. On the other hand, the element chlorine, usually in a gaseous state, is poisonous. However, scientists use small amounts of chlorine to purify our drinking water and keep swimming pools free of bacteria. However, when chlorine is combined with sodium, the two elements form sodium chloride, a compound commonly known as table salt, which is often used to enhance the flavor of food. Why is sodium chloride, table salt, a compound? Because its two elements are chemically combined and differ in both chemical and physical characteristics from the two elements, that is, sodium and chlorine, that compose its structure.
We're all familiar with the substance water, one of the most important chemicals for sustaining life on this planet. Here, we see the chemical formula for water. Chemists use such formulas as a shorthand method to tell us what elements make up a compound. This formula suggests that the compound water is composed of two elements, hydrogen and oxygen, represented by the symbols H and O. We can separate the elements that make up water through a process known as electrolysis, where an electric current is passed through a sample of water. During this process, the elements hydrogen and oxygen are separated from the water and are collected in glass tubes. Notice what happens when a red-hot splint of wood is inserted into the test tube containing oxygen. The wood bursts into flame. And now there is a popping sound, a small explosion, when we place the lighted splint near the mouth of the test tube containing hydrogen. So as we've witnessed, both these elements, hydrogen and oxygen, which exist in nature as gases, are highly explosive. Yet when chemically combined, these two elements form the liquid compound water, which is used to put out fire and is one of the most important chemicals needed to sustain life on our planet.
Another characteristic of compounds is that by ordinary physical methods, you cannot separate the atoms that make up the compound. Remember that we had to use a strong electrical current to separate the elements in water. You can freeze water to ice, boil it to a vapor, or leave it at room temperature as a liquid. But no matter what form, using simple physical methods, it remains as water.
Mixtures are another example of combined substances. But mixtures, like sandy water, don't have a definite composition and are not chemically combined. In fact, chemists are unable to write a chemical formula for a mixture. But using fairly simple techniques, you can separate the chemical substances in a mixture. How would you separate the sand from this water? To separate the sand from the water, we can filter the water through a strainer. Pizza is another example of a mixture, and using a fork or knife, you can easily separate the different parts of the pie, such as the dough, cheese, and toppings. Or let's suppose iron filings are placed in sand. Can you think of a physical process that will enable us to separate this mixture? One of the physical properties of iron is that it's magnetic. So, we can use a magnet to separate the iron from the sand.
Having looked at the phases of matter and seen the differences between elements, compounds, and mixtures, let's now turn our attention to some other unique properties of matter. When you watch an athletic contest, how do you tell the teams apart? You can tell the teams apart by certain properties they possess. In the case of this game, the property we observe is the color of the players' uniforms. In a similar way, chemists identify chemicals by unique traits or properties. For instance, properties such as odor, color, shape, and chemical composition are often unique and distinctive for a specific element or compound.
According to scientists, the melting and freezing points of a substance are among the useful properties that can be measured. Such physical properties allow us to observe or measure the substance without changing the composition of that material. With water, for example, we can record the temperature at which the water freezes and boils. Observe these two thermometers placed in freezing water and in boiling water. What are the freezing and boiling points of water? The recorded temperature for boiling is 100 degrees centigrade, and the recorded temperature for freezing is 0 degrees centigrade. Try to remember these temperatures because they are unique for water and can help us to identify an unknown substance as water, thus setting it apart from other liquids that may look the same.
Freezing, melting, and boiling, then, are the most common forms of physical changes. However, there are other physical properties that chemists find very useful. Here, for example, we have a teapot boiling, with water turning to steam or gas. Now, notice the water vapor hitting the cool surface of a mirror. How do you explain the beads of water on the mirror? As the gas or vapor hits the cool mirror, in a process known as condensation, the gaseous phase of water is turned back into the liquid phase. And here we have the opposite, rainwater on a sidewalk, which through evaporation will change to a gas as the sun heats up the surface. The amount of material that will dissolve in a liquid is still another example of a physical property. Through a process known as solubility, substances such as salt and flour dissolve at different rates in liquids like water. Does the flour we see here dissolve more quickly in the water? Or does the salt dissolve more quickly? Very little flour dissolves in the water, while the salt almost completely dissolves.
Physical changes do not alter the chemical composition of material. But during a process known as chemical change, chemical properties are altered and new substances are formed which bear little or no resemblance to the original substance. For example, chemical properties are changed when burning coal carbon combines with oxygen to form carbon dioxide. Or in a fireworks display, we see chemical properties altered when solid devices explode into colorful gases. To explain the physical states of a substance, such as a solid, liquid, or gas, scientists have suggested several theories. One such theory concerns how close the molecules in a substance are to each other. Here, for instance, we have two objects of equal size on a scale, but one is heavier than the other. How can you explain this? The blocks of iron and wood have the same volume, but the iron is heavier because its molecules are much closer together. Scientists call this physical trait density. According to chemists, the more closely packed the molecules, the higher the density.
To determine the density of an object, first, we must measure the amount of material in each substance, what scientists call mass. Mass is usually in grams or kilograms. The second consideration is volume. Volume is the amount of space an object takes up, and is usually measured in liters and milliliters for liquids, and cubic centimeters for solids. To get a better idea of what density means, observe what happens when we place water and oil in this container. Now, 3 minutes later, we see that the oil and water have separated. The oil has risen to the top of the container. Why do you think this has occurred? Since the oil has less density, it floats on top of the water. How can scientists use this knowledge to clean up an oil spill from a tanker?
The oil leaking from a shipwrecked tanker has less density than the surrounding water and will float on the surface, making it possible for technicians to contain the oil and then vacuum it from the surface of the water. With the blocks of wood and iron, since both objects occupy the same volume, the object with the greater mass, iron, has a greater density. Chemists calculate density with a simple formula. Density equals mass over volume. Using this formula, let's calculate the density for an object that occupies a volume of 4 cubic centimeters and has a mass of 2 grams, letting us arrive at this answer.
An object's density also depends on its state. For example, the molecules of gas in this container are not attached and can move about very quickly, spreading out and filling the container. Indeed, substances in a gaseous state can fill any container and generally have a low density. In chemistry, density is a property that helps identify different kinds of matter. Keeping this in mind, how would you compare the distance between molecules in solids, gases, and the liquids in these containers? The molecules are the closest in solids, which have the highest density among states of matter. Molecules are farthest away in gases. And in liquids, molecules are loosely attracted to each other. Since molecules in solids are tightly compressed, their motion is limited. So solids maintain their volume and shape. In liquids, molecules are further apart and slip past each other, but remain together because of various attractive forces, allowing a liquid to assume the shape of its container. This compression and movement of molecules is called the kinetic molecular model, and is also used by scientists to explain how materials are affected by temperature, as with this ball that fits through a ring. But then the ball is heated and will not fit. Why is this?
Because when heated, the molecules move further apart. Scientists refer to this property as thermal expansion. Bearing this factor in mind, why do you think bridges and sidewalks have expansion joints? Engineers use expansion joints to compensate for thermal expansion and prevent surface buckling in hot weather. Density, then, has a significant role in chemistry as an important property of matter.
Taking a moment now to review our work. During this program, we first took a look at the states or phases of matter.
Then, analyzed the structure of matter as evident in elements, compounds, and mixtures.
Before closing with a discussion of several unique properties of matter.
Most important, throughout the program, we have focused on chemicals as the basis for the richly varied world we live in.
To review the material we've covered, here's a final question for you to answer. Your teacher will discuss the answer with you after the program. Turn to activity sheet number 2, and we'll take a look at the question now.
How can we use a physical property of water to explain why we feel cooler, even chilly, when we come out of a pool or ocean water?
Go ahead now and complete the program. Later, you can discuss the answer with your teacher.